All right. Welcome to another Sunday session. For those of us in the U.S., it's Mother's Day, so I quickly said hi to my mom and Happy Mother's Day, and then jetted off to this book club. But I think, regardless of where you are, before we get into all the math, go thank your mom. They're fantastic people. They got you here. So happy Mother's Day for everyone on, and I hope you have a fantastic day with your family, no matter what we do. Hopefully, you're hearing sound now. Martine, I haven't seen you for a while, but I'm glad to see you here as well. It's been a bit. For the others, I've seen a lot of you last week. This is the fastest we've had a turnaround on this book club. 1 week. In some ways, it's good. I'm excited to be back. In some ways, it was hectic because it's like, I've got to set the live stream and everything up again. But we have it. I got the email, even though it was just 1 hour before. But you're all here. All right. So, as always, today is going to be a jam-packed session. We're just going to dive pretty much straight into it, talking about neural nets and code. No Google Slides this time. Just code. All the code is online on GitHub. You are welcome to follow along. I have to find it. GitHub. I think I put it in the email, but let's see if I can remember it from memory. Oh, first try. Almost never happens. You're welcome to grab this. This is going to be the repo we're going to be going through. But we are just going to jump straight in. So for folks who have been here and folks who haven't, I'll just give you the rundown. Let me bring my webcam up. Oh, I don't. Where is it? I guess I don't got it. There's always something that goes wrong every. I don't say wrong, but there's always something. All right, let's bring this up. There we go. Got to get all of this stuff working. For those who've been here before, you know the deal. For those who are new, ask questions anytime. I really enjoy questions. That's a lot of the value of this book club and study club, is that you folks can ask and we can interact. There's always a little bit of delay between when I'm speaking and when you see it, so don't feel shy. Don't feel like you have to wait for me to stop speaking. Just throw your questions in the chat and we will get going. So for today, let me do the quick overview of the study club. This is the topics we're going to go to over the next couple of sessions. Today is going to be getting into the details of neural networks, Flask, and model thinking. It's going to set the foundation for the more advanced architectures. So things you probably heard about: convolutional neural networks, recurrent neural networks. There's also LSTMs, which are sub-model architecture that's in there. There used to be these things. Well, there still is this thing called gated recurrent units. And then pretty much I feel like all of them have been blown away by transformers. So transformers are the things that you hear about all the time, whether it's the T and GPT, but also all these language models and generative models that we have. And then also variational autoencoders, which underlie image generators and things like that, which we will maybe talk about at the end of the book club. But all of that relies on libraries like Flask and PyTorch and TensorFlow, and all those build neural networks. So that's what we're going to talk about today. We're then going to get into the session after that is implementing a super basic GPT. We're going to follow a couple of tutorials on Jakarpathis and others, and you'll see how these transformer type networks work for text generation. After that will be probably the most interesting session. A lot of you posted in the community forum about this, actually. A ton of you, if I bring it up. A lot of you are really interested in how do people customize large language models, how to run your own and deploy them. Luke is asking about the hype, which is a very similar topic. So I think this session will be all about what is going on today. And when I say today, I actually mean a month from now, and a whole different set of things could be going on. So whether it's what models are out for use from the big companies, what is available to install and run locally, and how do you do it? How do you make the choices? How do I make the choices? Things like that. Every week, new things are coming out, whether it's like this week, Google announced its suite of really cool models. No bias, but I got to work on some of these, so I'm actually pretty proud of them. But the suite of models that Google has released in its systems, there's always new open source models coming out, so we'll talk about that in that session. And then once we know what's around, we can talk about shaping large language models to do what we want. It's a combination of prompt engineering or weights training or supervised fine-tuning or all these terms that you hear about. And then from there, we just maybe more. I mean, there's a lot going on in this space. So that's the overview of the entire club. Let me know what you think. I would love to know which topics you're most interested in the community or here. But before we get to all of that, we really should understand what's going on, because then it'll just make so much more sense about all these other things. Like way more sense about the pieces, the math, the computation, all of it. So annotated, today it's going to be what are these things really at their core. You're really going to just understand the lowest level bricks of these, like literally the bricks of this entire ecosystem. Now we have all these fantastic palaces and ecosystems and whatever, but what is the brick of all these models? The next one is how can we piece them together? So what are some older structures, and then what is the newest, sort of architecture for all these bricks we're going to learn about today. We're going to see how to train one of these ourselves and build it. We're going to build one of these ourselves. This one really is going to be a bunch of hot takes on my opinions about closed versus open source versus sort of open, large language models, and then making these work for us. So it's important to remember, aside from the hype, these are useful tools that we can use to do many things in our lives. Summarize text, generate creative poems for our mothers, write emails to our moms. We can use them to play games. There's a lot of capabilities that these things have, and we want to make them work for whatever we're doing, And so that's, rather than being subjected to AI, we can make AI be our friend. So today we're going to talk about the understanding of every basic part of a neural net. We're going to talk about the basic math. It's actually probably much more basic than you think. I'm just going to spoil it right now. It's basically just a linear regression. But then we're going to talk about the code. This is the most important one, because later on there's going to be a lot of code on the screen and a lot of things going on. And if you can understand how to read the code, then you have a really good understanding of what is happening in any various model architecture. So there's one level of understanding theory, but for me, I found that the best way to understand these models, frankly, hype-free, is when the model is available, just read the source code, or at least be able to glance through it, and then you'll know exactly what's happening. And then I think there's one other last bit, which is the mathematical ideas. So I know because people always tell me, they're like, oh, neural networks aren't Bayesian, or what, like, how come there's this tension, and they try and pit these ideas against each other. Frankly, I think all statistics is trying to solve, basically, the more I learn statistics, the more I'm just like, it's literally the same problem over and over again. Like, everybody is just trying to solve essentially a linear regression in the most scalable, informative, or efficient way. It's always one of the three. Whether you're doing Bayesian statistics, causal inference, or neural networks, it's literally, can I either make it scale? Can I get the most information out of it? And then can I make it easy? Like, you just take one of those dimensions, and then you just run in that direction, and then you get something. So if you're a Bayesian, you go, I want to get the most uncertainty and flexibility of my model construction, and that's the way you do linear regression. If you were in the causal inference book club, it's like, I just want to go from correlation to causation, and that's basically that entire field. And then the folks in the neural network side are basically like, how can I just scale this to be as massive as possible? And I know somebody's going to get offended at my gross simplifications there, but I feel like that's sort of the latent thing, and they all start with the same thing, which is a linear regression. So another spoiler for what we're going to talk about in about 1 minute. I don't know why I always wonder why the formatting breaks, so we'll look at it this way. So here's our plan for today. We're going to create some synthetic XY data. It'll cover some foundational SciPy or NumPy usage if you're not used to SciPy or NumPy. It's going to be a pretty rough intro to SciPy and NumPy though. We're going to use neural nets to recover the parameters, and through this parameter recovery study, you will understand how neural networks work. You'll just understand how these frameworks work, how to piece it together. And then we're going to do the same thing for a nonlinear data generating function. So what we're going to do is we're going to expand on we're going to move from our synthetic linear data, and what we're going to do is then go to a nonlinear function, because that's the important jump that really then just sets us off on the slope of all the crazy possibilities and all the cool things that neural networks can do. So I'm going to pause there. I've said a whole ton about Mother's Day, our study club, and our plan. Let me look at the chat super quick and see what folks are saying, and then we will dive back in. Gotta rearrange all these windows. Chat overlay. All right. Nitesh says, just finished reading your book. I have been using HLM after reading your book in a business problem which involves clustering data using Bambi. Okay, so HLM stands for hierarchical linear models. Super cool thing that Bayesian linear regression can do. And we're actually going to use Bambi today a little bit. So Nitish, we're going to talk more about the neural network side, but I, as you can tell, love hierarchical linear models. Thank you for reading my book. Someone on LinkedIn says, good study plan, wish you the best. I think the LinkedIn chat integration is not as good on this Restream platform, but I'm glad to hear that. All right, glad somebody is enjoying the study plan. All right, I'll let more questions come into the chat, but we are going to keep slamming through. I always try and keep these sessions, I always try and keep them under an hour, but I always end up being a little bit over an hour, so we're going to shoot for under an hour again. All right, so for today, here's the key points to remember. We're going to talk about the general intuition of how neural networks work. A big thing is how we define these models in Flex. Let me turn this chat overlay off. How we define these things in Flex. We're going to be using the Flex framework quite a bit in this study club. We can get into a whole thing about PyTorch and TensorFlow and stuff like that at the end, but I'm going to just tell you Flex is going to break the stuff apart in a way that makes it easier to teach, in my opinion. So we'll use Flex. And then I really want you to understand how these parameters are estimated in a neural network. So the loss function, how we construct that, which includes the metric that we use, and then the usage of OptX, the optimization algorithm or library that we're using. Because if you understand these things, you'll understand how these things are trained, which will become important for the next sessions and is important in neural network practice in general. The other way we can do this club, and I don't mean this as a good way, is if you don't want to listen to me talk and you don't like the live sessions, that's totally okay. These are the references that I think are most important for this session, and if you go through and read them, you will have an equivalent understanding of this entire next 40 minutes. So you don't have to listen to you don't have to listen to me talk if you don't want to, because a lot of other people have done really, really great things, and I want to point out we're going to be leveraging a lot of other people's work, and a lot of this book club is just going to be me summarizing things that folks have already put out there in the world. Now, I will say maybe the one benefit of me explaining it is that there is so much content out there that I'm going to give you what I think is the most succinct and straightforward and the best. So for this week, these are the three. It's this blog post from Joshua. Sebastian Rashka, who is quite a good leader in this space, has a lot of content between his book and his video courses. And this is a link to a specific video in his overall course, but his overall course is also really good. And then the Flax documentation. We're going to be using the Flax documentation a lot throughout these sessions. All right. So in this first part, we are not going to be modeling anything. I want to point out for the next 5 minutes or so, there is going to be no neural networks, no Bayesian statistics. It's just generating data. The reason I'm generating data is when you generate data, you know the underlying parameters. So then when you run a model, you know what the parameters should be. The alternative to not generating data is answering a real world problem with real world data. The pro there is it's cool because you're solving the problem. It's interesting to come to conclusions, but the downside is you don't actually know what the true parameters are going to be. So because we're working on the basics in neural nets, we're going to generate our own data and then see whether we can recover the parameters. This is called a parameter recovery study. It's a really useful thing that I just don't think enough people do in machine learning, causal inference, or Bayesian statistics, whatever it may be. When you're learning about a new model, a new architecture, a new library, like whatever it'll be, it's good to generate your own data because you know what's going on, see if you can recover the effect, and if you can't and it doesn't make sense, then you need to learn more. We do data generating stuff in all my courses. Scott Cunningham did a bunch of data generating stuff in the causal inference book. Richard McElrath does a bunch of data generating stuff in his book, and I always love people who do that, so we're going to keep doing that here. All right, so generating data. What we're going to do, and this is going to be the basis for this entire the entire rest of this session, is we're going to generate data for a linear regression. Y equals mx plus b is the way you see it when you work or when you're studying in grade school, and we're going to just take it up one tiny level by having two regression coefficients. We're going to have m0, m1 multiplied by x0 and x1. We're going to have a bias or an intercept, as they call it, and then we're going to be estimating y. So y is our output. We have two things that we can observe, and then we have two coefficients we're trying to recover, and technically a third coefficient or bias that we're trying to recover as well. So this is it for today in terms of the complexity of our model. We're really, again, starting out with the basics. So on this slide, all I'm doing is I'm setting the numbers. I'm setting our first number to be 1.1, our second one to be 2.1, and then our intercept or our bias to be 3.1. Now what I'm doing is I'm going to take our coefficients and I'm going to put them into arrays. This is something you're just going to have to get really comfortable with, and it's I don't want to say it's the hardest part about these neural network stuff, but it is really knowing the shape of your arrays. We're going to talk about this probably 6 or 7 times today. You're probably going to get really sick of me hearing this, but if you're going to practice with neural networks and you're going to use them yourselves, you have to really, really know the shapes for a lot of reasons. So what you're seeing here, and go back to it, is I'm putting this in a very specific shape that is going to be important for our code to work. So now that we have our coefficients in our array, so here, this is 0, 0, and this is 0, 1, because the first index is 0, and then the index within here is 1. We can then plug in just any arbitrary values of x1 and x2, and we get our numbers back. So see if you can do the math in your head, but 1.1 plus 3.1 is 4.2. 2.1 plus 3.1 is 5.2. And that's the numbers that you're seeing here, right? Very basic, again, like grade level school math, but now just done in NumPy and SciPy. These x1s and x2, I just picked completely arbitrarily. I happened to pick them to make it easy for us to do the math. But in the real world, these would be our observations. So I think I have this later in here, but maybe the way to think about this, if you like real world framings, is we're trying to estimate the weight of somebody. So all of us have a height, like how tall we are. All of us have a width, about, how wide we are, and then we have a weight. So if I came up to any one of you, I could measure your width, and maybe let's say that's x0. Maybe I'll measure your height. Let's say that's x1. And then there's some coefficients where I can multiply and then get your weight. Maybe your, let's say kilograms. You're 50 kilograms, 60 kilograms. Maybe that's our real world problem here. So maybe I measure the height of somebody that's 0 centimeters tall and 1 centimeter wide, and then 1 centimeter tall and 0 centimeters wide, and these are the numbers I get. let me get out of the code for this one. So here's what we get. Because we have two coefficients, we have m1 and we have two dimensions in our inputs, x0 and x1. We end up with a plane. If I took our function and I put it in, we get this plane that looks like this. So this is still linear, but it's linear in 2 dimensions, and that's the surface that we're estimating on top of. So the next thing I'm going to do is I'm going to generate random x1 and x0 points. In real life, you don't if you could see the plane, that would be the best, but you don't. You get random points based off of that picture, and from those random points, you need to then estimate everything else. You need to estimate the coefficients and then the unobserved y's or whatever it may be. So all I'm doing here is I'm going to generate 200 random observations. Let's say this is 200 random people that we've pulled off the street, and we measure their height and their width. You can grab those random things, those random observations, and then you get your y observations, let's say. Because this is a synthetic study, I am calculating the y observation myself, but in real life, you would just get this from your actual data. So here we have our shapes. I'm going to point this out again. The first practical tip I have for you is shapes matter a lot. So what we have here is we have our coefficients have shapes 1 and 2, but our observations have shapes 200 and 2. Okay. So in our model, we have 2 parameters, and that's why we have the shapes 1 and 2. The 1 just being that the leading number that we just have an array that is 1, and then the 2 being the number of coefficients we have, and then the observations being we have 200 observations of 2 things that are going into that are our independent variables, like our height and our width. You're going to hear me try and explain shapes a lot because they're going to keep coming up over and over again. The reason we have to have a more complicated shape for the coefficients rather than it just being a vector of 2 comma is because I want to show you how matrix multiplication works. In a lot of neural network tutorials, you're going to see a linear regression represented like this. You won't see it represented like the piecewise thing that I've done. You'll see a lot of tutorials do this matrix multiplication. Matrix multiplications are all over the place in neural networks, but I'm not going to go into depth into matrix multiplications here because once you start using neural network frameworks, you are not doing the matrix multiplication yourself. So my advice at this point is if you're looking to learn a ton about neural networks and start with the really basics, you're going to see a lot of matrix multiplications from Andrew Ng's course and others. But if you are just going to use Flax, which is the approach we're going to take, you're not going to see me do matrix multiplications probably ever again in this study club. Just know that under the hood, a matrix multiplication happens a lot in neural networks. The reason this matters is in matrix multiplications, I should make this just a little wider. In matrix multiplications, what happens is you have these what's called contracting dimensions. They cancel out, and then you end up getting the thing that you want, which is the y observations. So what we're looking for is 200 observations of y, and the way we get it from our coefficient matrix and our x observation matrix, our input observation matrix, is like this. These 2 dimensions cancel out, and you get that. Another practical tip or an aside is if you're doing this matrix multiplications a lot in NumPy or SciPy, einsums are one of my favorite ways to do this because there are a lot of ways to multiply matrices, just so you know. There's inner products, outer products, dot products, determinants, all sorts of things. And rather than remembering the API for everything, this einsum API is common across SciPy, TensorFlow, and PyTorch. So it makes it easy to switch between the frameworks, but still get all the things right. Okay. The next thing I need to do, just as another aside, is just add some random noise to y. This is because in the real world, you'll never get the perfect measurement from your x coefficient to your y coefficient where everything matches. So just to make this a little bit more realistic, we're just going to add some random noise. This is just a good thing to do when you're generating synthetic data, because there's a lot of algorithms that can work really well when there's no noise, but when there is noise, maybe their results worsen, and so it's good to have that in your synthetic data studies, so you can just test out the effect of not only your model construction but also its sensitivity to random noise of any type. I happen to use in this case normal noise, which is like the common assumption, but I would advise, especially in things that are particularly important, to test out what happens when your noise is not normal. But I've said a whole ton, so let me just recap what we've done so far. I invite you to ask questions now while I'm talking, because if any of this was confusing or you want any more details, it'll help you with the rest of the study session when we get into the actual modeling, which we have not done yet. So just super quick recap. We've just defined the data generating function for which we have generated data for, and our goal is to recover these three coefficients, M1, M0, M1, and the bias or intercept. We've picked some totally random numbers, 1.1, 2.1, 3.1, just to see if we can get them. Generated some random observations just to have something to work with. We used those to calculate y, and then we added some random noise to y. We haven't done any modeling yet, which is going to be the next step. So our goal for the rest of this club, X1. Our goal for the rest of this session is to show how you can recover these using a neural network framework. But I want to point out that this is maybe the first thing that makes it like confusing and the first point where I don't understand why people pit these things against each other. But there's a lot of ways we can do this, right? We can do this with linear regression, like the grade school way. We can do this with machine learning, like a scikit library. We can do this with Bayesian regression. We can do this with neural nets. It's not that when you're doing neural networks, you're just doing something that's completely different than what Bayesian people do, or different than the XGBoost people who are doing machine learning. Like, there's not these sort of divides where all these mathematicians are pitted against each other. It's just that, like I said before, we're just solving different. I don't want to say different problems because we all care about the same things, but we're just using different approaches that either scale a different way, give us different information, or work in a framework that we're working with. So to give you that, an example is for this first one, I'm going to recover these parameters just using Bambi. Where is my all right. Always problems with live coding. What I'm going to do is I'm going to show you this with Bambi, so you can see that the way we're recovering parameters. So what I can do in Bambi is I can set up a model that looks like this. Y is a function of x0 and x1. Bambi automatically makes all the coefficients. I did it here twice for some reason, so just ignore that for a second. But here we get our parameters. Essentially, we get 1.1, 2.1, 3.1. We get a trace plot. We get noise. You can see the numbers basically here. So to reinforce the point, we're gonna cover this regression using neural networks and Flask in just a moment here. But it's not like when you're working on neural networks that couldn't be Bayesian or couldn't be causal inference or couldn't be this or couldn't be that. I want to highlight there's not really this artificial distinction that I sometimes hear a lot. You can use a lot of different approaches and methods to do the same thing, but as you know, neural networks are able to scale and do really cool things that we're not able just to do in Bayesian networks at the moment. So as we go through this book club, study club, I'm gonna point out that there's no reason there couldn't be Bayesian neural networks other than it's not computationally feasible right now. There's no reason maybe we couldn't do causal inference in neural networks. We just haven't figured out scalable or ways now. But there are people that are actively doing research to take the coolest things that we're learning in neural networks and move them all over the place. And it's actually one of the reasons I'm doing this book club. It's because you can take these ideas and spread them into different places. And the more people that understand what's going on, the more these ideas can spread, and we can join efforts and mix and match different parts of the modeling ecosystem. All right. So now that we've sufficiently used at least Bambi to recover our parameters, what we're now going to do is we're going to move into what we all came here for, which is the neural network portion of our study club. So we're going to flip back and forth between slides. Actually, it just looks like, if you can over here, this window is frozen. So we're going to jump back into slides. Maybe we won't jump back into slides because now things are going to get really long. All right. So at their core, neural networks are just linear regression as well. This is a really, really big simplification that we're gonna then loosen later on. But the neural networks, just honestly, at their core, are just regressions at each layer. You're just taking a bunch of inputs, you apply them by you take a bunch of weights, you multiply them together, you add in the bias, and then you get some sort of output. That's the core of it, and I'll show it to you in Flax. Here you see the matrix multiplication syntax, which is why I showed you the matrix multiplication at the top. But a bunch of weights, your observations, a bias, you get an output. This particular graphic I took from Joshua's blog, so credit to Joshua. And you see Joshua has the exact same formula that we had at the top as well. What we're gonna do now is we're gonna create a neural network in Flax. So I'm just gonna show it to you just straight off the bat, and then we're gonna talk about each individual piece. So from this point out, what we're gonna cover, and the mentality I would like you folks to take, is I'm gonna show you the model definition, and then I'm gonna show you every single piece of how we end up to the exact answer. Because defining the model is just one thing, but you have to then input data in the correct way. You have to be able to understand a lot common loss functions, how those loss functions get optimized, and then how to look at the outputs. And then particularly with neural networks, we're going to talk about things like checkpointing and epochs, because these are common terms that keep coming up with neural networks, especially these large language models. And so by seeing it in a very simple circumstance and getting a sense of how to read these things, when we go to next week's session about convolutional neural networks and transformers or things like that, you won't then be lost in the training and parameter sides of it, and we can focus in on just the model side of it. So in Flax, which is the neural network framework we're going to be using, this is how you define a linear regression of the same form that we had just shown before. What you do is you create a class, you submodule neural network module. In the setup call pattern of Flax, you define your architecture right here, and then you define your actual computation in this block down below. What we're doing is we're setting up what's called a dense layer. Next week we'll talk more about a dense, I'll show you a picture and stuff of what a dense layer is. But for now, just think of it like a fully connected linear regression where everything is being used, as you'll see in a second. We pass our x values to this dense function, we get a prediction, and then we get a linear regression. This is all that's needed in Flax to define a model. Now, the next thing to know about Flax and why I chose it as the training framework is in Flax, the model itself doesn't have the loss function we'll see in a second. It doesn't actually have the parameters or the state. It doesn't store any randomness in the model itself. Flax is built on top of JAX, which is the thing we use in the Dynamax book club. And so what we need to do in Flax is we need to set the random state of our world somewhere else. We'll talk about where the randomness comes in, but whether you're Bayesian or whether you're working with neural nets or whether you're frequentist, there always is some randomness that needs to be incorporated either in your data or in your training process, and capturing that is important. So here we set the key for our randomness. So the next step about training neural networks is you have to initialize your parameters somewhere. So this is where Bayesian frameworks, let's say, and neural network frameworks diverge when you're talking about, let's say, traditional neural network training. In Bayesian networks, you have a prior, and what you say is everything is possible, but they're possible with different degrees of probability. That works really well when you're using MCMC and solvers and in that sort of framework. But what we want to do in a neural networks type training, in this case, is you just say, I'm going to start somewhere randomly in the world, and I'm going to see how bad it is. So rather than saying I see the entire world and I know before I see any data how bad things may be or may not be, the idea here is you just say I'm going to just pick a random point and I'm just going to start seeing how bad that potential case might be. At this point, we don't have a measure of how bad things are. We just have the random starting point. So with this random key, what we do in Flax, and this is a fun part about Flax, is you don't need to define the shape of your inputs. You just give it the randomness, you give it the X observation, and Flax goes, okay, with this random key, and I can see with 2 random observations, I need to generate 2 coefficients, and I need to create 1 bias parameter. Flax just auto-magically knows this. This is a huge benefit of using neural network frameworks, especially when we get to bigger and bigger models. You don't need to be defining the shape of every single size of array. It gets very tedious and repetitive. It's a huge reason people use these frameworks. One of the big reasons people use these frameworks rather than use NumPy or SciPy by hand. So all we need to do is pass in our observations, and it just knows. Like Flax just knows that we need 2 coefficients. This is fantastic. It's super nice. Another nice feature of Flax in the neural network frameworks is you can print out the architecture of the models. So right now we have 3 parameters. We have our M0, M1, and bias. In working with these large language models, you frequently see things like models have 64 billion parameters or 5 billion parameters, or like literal billions of parameters, this many million or that many million. We're going to get to this again later in the book club, but when you see people talk about model sizes, this is what they're talking about. Oops, not that. This is what they're talking about. They're talking about how many parameters are being estimated in the model, and we're doing a simple neural network of 3, but the big models have literal billions of parameters that they're estimating. People argue about whether it's a good measure or not, like for cars, whether horsepower is a good measure or not, but it is currently one of the most common measures you'll see when working with large language models, the number of parameters that are in that model. Now the next thing we can do, just to show you how Flax works, is we can just take any random x and x1 and x2. So in this case, I chose 1 and 0 like we had before. We take our model, we take our parameters, which are stored in this object outside of the model. We pass in a particular x value, and we get our prediction. So for 1 and 0, we get right now a prediction of 0.23 as the value. We know that this is not what should happen, because if we go all the way back to the beginning, where we already did this ourselves, we should be getting 4.2. But right now, with an untrained neural network with just random parameters, we're getting a value of 0.23, and we have to figure out how to get this to be the correct Y output. The parts I want you to know, I'm going to highlight again because these are the details that we're going to be going on over and over again. In Flax, you have a model object that defines the architecture of your model, as shown here. You have parameters that are outside of the model, as shown here. These are currently random. And then you can pass in any x using apply function, and then you get your output. So this is how we can make predictions later. We're going to be passing things into the apply method on the model. We're going to pass in parameters, and we're going to get our outputs. This is called a forward pass when you talk about neural networks, because you're taking your you're taking your inputs and you're running them forward through the model to get an output. All right. Aiden asks, will this be available to view later? Aiden, all of this is available on GitHub, so you can just look at it. You can look at this now if you'd like. Grab it and go ahead. I know, again, I'm going pretty quick because the goal here is to provide an overview within an hour. And then in this particular study club, we leverage the asynchronous community forum to talk between sessions and reinforce our understanding. All right, so let's move on to the next thing. So far, I'm going to point out what we have done is we have generated synthetic data. That's not modeling. That's just us setting up our scenarios so we can have something to work with. In the real world, you might find some data that you're working with, but here we want to generate our data so we know how to get back to the parameters that we set at the beginning and verify we did everything correctly. The next thing we did, it was just a quick aside to show you that there shouldn't be this fight between Bayesians and causal inference people and frequentists and deep learning people. Like, we're all really trying to do just the same thing. And you can use a Bayesian framework to estimate these parameters. But that just sets up a comparison to what we're doing now, which is setting up a model and doing estimation in a neural network framework. So we set it up and we made our estimation in a Bayesian framework. So here's how we set up our model using Bambi in a Bayesian framework. Here's how we estimated our parameters using MCMC and a bunch of terms that I won't get into in this book club using Bambi to get back to our 3.1, 1.1, and our noise. And here's how we're setting up our model in Flax. Here's how we generated our random parameters that are starting point. And now we're going to get to how we're going to train. So it's great to have the neural network. It's great to have a random set of parameters for it. But really, with a random set of parameters and even the best neural network framework in the world, your text generation or your images or whatever are not going to look good. You'll see this in the next session or 2 sessions from now. But when you have random parameters, you really literally get random results, and they're not really that impressive. If ChatGPT or Bard just gave you random strings of text, like, nobody would care. They wouldn't. It would not be that fun to work with. So what we need to do is we need to estimate the parameters of our neural network in some way, and the most common way to do that in these larger frameworks is using gradient descent. And so let me show you the visual. This particular blog post does a fantastic job, and I won't talk through the details of it, but I just want you to know what's essentially happening is we're going to be setting up what's essentially a surface, and we're going to be defining the surface with a loss function. So when things are really lossy, that surface is going to be really high. We're going to get outputs that are way high up here, and we're going to know they're terrible. But as our model trains and changes parameters and makes estimations, the loss is going to get lower and lower and lower, and we're going to try and get to this local minima. So commonly in neural networks trainings, you'll see these loss epoch curves. You're going to see a couple of them later, and you're going to see how as the model tends to get better and better at predictions, this loss epoch curve tends to go down. But what we first need to do, is define this surface. So the way to do this is you have to first pick a loss function. So you have to decide what you're gonna pick. In our case, we're gonna use L2 loss because we're doing a linear problem. Later on in text generation, you'll see that we'll pick another one. But for now, we're using L2 loss. This is called mean squared error. And I'm gonna show you how to do this by hand. So let's take the parameters out of our model. In this case, I'm gonna take the params out of our Python dictionary. So params, dents, kernel, and here are 2 random coefficients. These are not observations, these are coefficients. I'm gonna take our model. Well, maybe I should have named this a little bit differently. I guess it's okay. So I'm gonna take our coefficient M0, I'm gonna multiply it by our first observation. I'm gonna take our coefficient M1, I'm gonna multiply it by the second portion of our first observation, add the bias in. The number we should be getting is 4.5, but we're actually getting a different number. The number we were getting was right here, 0.23. I'm sorry. We should not be compared. I apologize. What we're getting here is this is our prediction. We match that up against our observation, and then we end up with this particular loss function. So I'm going to do a dangerous thing here, and I'm going to run my code, and I'm going to hope it doesn't break. So this is going to be the make it or break it section of our book club. Let me run everything above. Hope it all works out. Fingers crossed. Good time for questions. Let's see where we're at. All right, not too long. We should be getting there. All right, we're back. We're back. Okay, so here's our prediction from our model. Here's our actual observation. So if we take the parameters from our model and we make a prediction, right now our prediction is 4.57. What our actual observation is in the real world was -10. These numbers are not very close together. This is not so fun. So we're going to define our L2 loss, and this number here represents how bad our prediction is. Because we're taking our prediction, we're taking our observation, we subtract them, and then we square them and divide them by 2, and we get 115. The obvious question is, why do we do all of this? It's because we picked the L2 loss. That just happens to be the loss function that we picked. There's no truth in the world that this has to be the loss function. This is our choice. We then run it through what the definition of that loss function is. In this case, the L2 loss happens to be the squared error. The divided by 2 is just a historical artifact that shows up, but it is just there because it was defined there like 30, 40, 50 years ago, and we just do it now. Everybody just does it, and we get 115. Now, defining these things by hand is annoying for 2 reasons. One is it's actually very easy to mess this thing up, and then if you mess this up, all of your math is wrong. Like all of your code is wrong, so it's very annoying to do that. The second reason defining it by hand is annoying is when you're doing it like this in pure Python, you're calculating this thing over and over and over and over again every time we're training neural networks or whatever it may be. So this is slow if we do it this way. So what we want to do instead is not do all of this by hand. Doing all this by hand is a huge pain. It would take forever. So we want to make our calculations and our predictions in our model, which is what we do here, and we get the same number. But we also then want to use Opdax, which is a different library in the JAX ecosystem, to then calculate the same loss. So rather than do everything by hand, use Flax and use Opdax. Flax defines your models. It lets you do the forward computation. Opdax has a ton of loss metrics, like a ton of loss metrics. And Opdax, I don't know, we're using Bing. I should not, but anyhow, Opdax has a ton of optimizers, like a lot of them. That's the name of the library. So you're going to be seeing us use Opdax a lot in this particular club, but it's also whether you're using PyTorch or TensorFlow or whatever you want. These are the exact same algorithms that are available in all of the other libraries. All right. So another recap. What have we done to this point? We've defined our model. We've generated random data. We've defined our model architecture, which lets us then make predictions. But we have random parameters which don't make very good predictions. You just saw that. Our predictions are quite far off. So what we need to do is we need to define a loss surface. The way we did that is by picking the L2 loss metric, completely arbitrary again. It's what we choose. We could have chosen any other loss metric, but we happen to choose this one. And with that, we now know how bad our predictions are. So now we know how bad our predictions are. What we want to next do is make them better, right? Like we want to get to a point where our predictions are better. The way you do that is by getting back to getting to the optimal parameters. In this case, we know what our optimal parameters are because we pick those parameters in our data generating function. but we want to have our neural network be able to do that itself. Now this is called training. So the thing we're going to do next is from Flax, we're going to import train state. You're going to see this in the next sessions as well. You're going to see me define a model in Flax. You're going to see us pick a loss function in Optax. And once we've done those two things, we're then going to train the model. And in Flax, we import train state. This is a very common pattern in Flax where you take your Optax function, you take a function, you wrap it in this sort of training function that takes the parameters, your x, your true y. In that function, it makes a prediction, and then it returns a total loss over all of your x's. We also what's called jet this function, which is just-in-time compile, because we're going to be calling this function a lot, like many literal thousands of times. And we want to make this computation as fast as possible. So the mathematical things that are happening here again is we are taking our loss function and wrapping it into a Python function that makes it easy to call from in the Flax training loop, which we'll see again in a moment. And we're jitting that function so it's really fast. Even I'm going so fast, and I'm gonna recalibrate my train. Okay, a thought. The next common pattern you see is you have to decide how far of a step to take. So if we look at our visual once again, a lot of math goes not even just like in neural network training. A lot of research that goes not into the models itself, not into the data, not into the loss functions, but literally how to take steps along this function. Each one of these balls is taking a different function or a different method of how to take steps. And you can see some of them speed into certain holes, some of them going a little bit slowly. And a really important point is if you pick a different one, they can take different paths into different local optima. So anybody in this room could literally get an entire PhD just in training step functions for optimization. And you could get a PhD in any one of the other steps that we talked about as well, by the way, whether it be data or whether it be the model or whether it be loss functions. So each of these is a key study portion that people can spend their entire lives just studying. And that's what we're defining here at, I shouldn't flip between, too many tabs, huh? Too far. That's what we're defining here. We're going to be defining, this optimizer is setting our learning rate. So we have to now pick how fast we move down this particular set of curves. And you take all of that, everything we did below, and you pass that to Flax and you put it into a train state. So you pass in the models, you pass in the parameters, you pass in the optimizers, which then gets you a train state. And with all of that, we get to our actual training. So here we are taking our train state that we have set up above right here. We're taking our model, which is in that state. We're taking the parameters, which we are updating, and then our X observations and our Y observations. And then also our Flax L2 loss includes this in it as well. What I advise you to do, and especially if you're going to continue on this book club, is get really good at understanding this block, because this is where it all comes together. It's the model, the loss function, the step optimizer, the parameters, and then the train state. And if you understand the relations between all those things, all these Flax loops will make sense to you. The reason I chose Flax as our learning sort of framework is it does the best job of separating all these things out. I feel like a challenge in the other libraries, which is like PyTorch and TensorFlow, is it makes it easier to put all these things together and store all these things in one sort of model object and pass along the loss and everything like that. But when you're learning, it then becomes, the boundaries between these things become unclear, right? Because they're all mushed together into one Python object. I appreciate how Flax splits these apart. Now, does this make it annoying because you have to remember all these different objects and wire them together in this functional neural network pattern? The argument a lot of people can make is yes, like it gets annoying and you have to remember all the names and you really could have just put them all together. But for the purposes of this club and for the purposes of learning, the separation and the distinction, I think, really reinforces the idea that they are separate things that you need to have different ways of thinking about when building neural networks. All right. So what we're gonna do, what's happening here is where training is happening in your neural network. So if you were Bayesian, this is what we would call maybe the MC sampling, right? This is where you're estimating your parameters. In neural networks, and especially in Flax, this is where we are estimating our parameters. What we're doing is we're taking our loss function, we're seeing how bad our predictions are, and then we're recording that, and then we're taking a step with our gradients. So this is what's called gradient descent. We're looking at what's the fastest way we can get to a lower level of loss. We take that step. The length of that step is depending on the step optimizer that we're using. And then we go back and we measure our loss again, and we keep doing that. So here is our training loss. This is a very, very important plot when you're training neural networks. We're seeing how crappy our predictions are at the beginning. In this case, the high number means they're particularly poor. And then we are making each step, we're getting closer and closer and closer to the right set of parameters that's making our model better and better and better. And then at some point, our model's not getting any better in this case because we've reached the optimal point. And when you take a look and we go back, we get pretty much our exact numbers. So at our final state, after all of our looping, we end up with 3.1, 1.1, or sorry, we end up with parameters that make our model fit particularly well. Now there's something here that I'm not gonna mention for a second, but I'm just gonna tell you that there's something about these three that's different from our initial parameters, and we still get really good estimation. I'm not gonna tell you what it is till the very end of the book club, but if somebody knows what it is, you should put it in the chat. Compare the numbers above, compare these numbers, and tell me that even though these numbers are pretty close, what is subtly off about them. A lot of typos here on book club. Parameters. All right. Cool. So let me do my recap before I get to the very last section, which is nonlinear data. What we're doing here is what every statistician and every machine learning person and every neural net person and every deep learning person in the world is trying to do. We have some data that we've seen in the world, okay? It could be a linear regression, it could be text, it could be images, it could be the usage of methamphetamine and policy from people. Like, that's what we covered in that book club. It could be planes that are flying through the world and we're trying to figure out where that plane is. It could be I launched a rocket and I'm trying to figure out where my rocket is. Everybody in the world is trying to do the same thing, which is they see the world, define a model, and then estimate the parameters of this model. Now, the ways we do it are just different. So it's not, in this case, with neural networks, the ways we do it are by setting up models in Flax and JAX and PyTorch and TensorFlow, and then estimating our models using the tools we have here. So to recap the tools that we use for neural networks, we set up our linear model in a neural network framework. So instead of using a probabilistic programming language like Bambi or PrimeC, we used a neural network framework, which was Flax in this case. Because we're going down the neural network path of estimating parameters, we had to pick a loss function. We had to use an optimizer to go through those steps, and then we estimate our parameters using a training loop that we have shown here. And what we get at the end is that we get parameters, but we don't get uncertainty. So if the Bayesian part of me was saying this, I would be happy that I would be sad that we don't have uncertainty, but I would be happy that we were able to train this. I want to point out that whether we use Bambi or whether we use Flax, we get essentially the same parameters. But in this case, we don't get uncertainty. In the Bayesian case, we do get uncertainty. But later on, as you'll see, in the Bayesian framework, we would never get any answers if we used MCMC to solve large neural networks. But we do get answers if we use the these computational tools and frameworks. But the loss of uncertainty is actually really important and something that is a big issue in actually a huge issue in the current neural network paradigms, especially for things that you really need uncertainty for. All right. Now that we've covered model thinking, I want to give you one subtle twist to show you what happens if the data is nonlinear, because this is the motivating case for the entire rest of the session. Because as you can tell, we don't really need neural networks to train linear regression at all. This was probably like shooting a fly with a bazooka type of thing. There are way faster ways to get linear regressions in Python, but it's the motivation of getting to things that are nonlinear. So if our data is nonlinear, it's going to look like this, right? We're going to end up with a curve that looks like, say, this parabola. We can do the same thing that we did before. We just take our model and initialize some parameters. Now, what I want to show you here is we need to reshape x. You should try. Sorry. Let me start this over again. We can take our model. We can pass in x nonlinear. But what happens is we end up with 100 parameters, which is wrong. That's an issue because we don't want 100 parameters. We want one, actually, in this case. We only have one parameter in this model. And to back this up even more, this is different than our previous case because this is a 1D function. Sorry. There's only one x in this function. There isn't two. There isn't x1 and an x0 and an x1. We literally just have one observation and we get one output. So 1, negative 7.5, we get this number. 2.5, we get this number. 7.5, we get this number. But if you do the thing, which is the knee-jerk thing to do, is you just pass it in by itself, you get 100 parameters, and that's not what we're looking for. We're looking to estimate one parameter. So again, I'm going to highlight the practical tip of really, really, really look at your parameter shapes. Like, always be looking at your parameter shapes and making sure that they make sense. It does not make sense that we have 100 parameters in our neural network estimator. We are trying to estimate one parameter. So what we're going to do is we're going to reshape x into this column, this type of vector here. And now we end up with, I should have said two parameters. We end up with one coefficient and one bias, not 100 coefficients and one bias. So we go through the same thing that we did before. Now that we have our data, we set up a train state. We use the same L2 loss. We just happen to pick the same one. We do this because we want our shapes to be correct. And then we end up with a number. We end up with a train state of 9.8, negative 7 point whatever. We take our data, we make predictions, and we get a fit, and it is a terrible fit. Like, this fit is miserably bad. Why is it bad? Because we're trying to fit a linear model to a nonlinear set of data. The model did the best that it could in the constraints that it had, but there's no way it would have been able to fit this because it's just too constrained. When we go to the next sessions next week, this is going to be the thing that we're going to be talking about, right? It's how do we pick certain model architectures that can fit our data? In some cases, convolutional neural networks are able to fit certain types of data pretty well. In other cases, recurrent neural networks can fit other types of data really well. It's all about creating models that can fit the shape of our data. And in this case, our model could not fit the shape of our data. Like, it does a pretty crappy job. So how do we make this nonlinear? Now, I'm not going to go through the specific details on this particular session, but in neural networks, what happens is you start adding layers. If you start adding layers and blocks and self-attention blocks and kernels and all sorts of things, you start adding activation functions and tons of different things. So one way you can do it is you can, in Flax, is you can set it up like this. Another way is you can use this compact syntax. So Flax offers two different layers and two different ways of doing this. I want to point out these are not the same models. I should have made them the same models, but they are not. But they are just two examples of how to set neural networks up differently. What we're going to be working with is this one, where we've set up what's called a dense neural network with a dense layer with 128 parameters, We're passing it through a certain activation function, which is a term we're going to talk about next week. And then we're going to get one output out at the end. And because we do this, we end up with a ton more parameters than we have in our previous model. Like many, many, many more parameters and a much larger kernel and bias and whatnot than we had in our previous model. But we go through the same steps as before. We pass our train state. We use our test train. We set up a training state. We set up our training loop, which takes our model and our parameters, makes an estimation of what the true value should be. We measure our loss. We then measure the gradient of that loss as well. And then we move one step with our parameters to try and make our predictions better. And if we do that a lot, we end up again with another step or epoch or training loss. We calculate our predictions, and then we get a neural net. Then we get our predictions, and in this case, our predictions look pretty good. Now, what I want to show you as we do as the last live demo before we're done with this session is, let's say we don't quite train our model all the way. Let's say we just do 10 epochs. I need to run this all above. What I want to show you here is checkpointing and how the model trains over time. So another good way to build intuition about neural networks, and it's a pretty common tool, it's you train your model, you get to a certain point, you look at it, and then you start with those weights, and then you train it some more. This is called checkpointing, or it's also called snapshotted weights. And I want to show it to you here because this is going to be a key piece of understanding we're going to use later on in the rest of the book club. A lot of you folks were asking about how do I make these models useful for myself? This is pretty much what is happening in open source right now. It is that companies are releasing their set of weights that they train to a particular point. And then what you can do is you can take your own data and then start retraining the model from that starting point with those weights, and then sort of then shift it towards where you want it to go. So it's this really fascinating method of what they call pre-training. Well, it's in the GPT name, but like pre-training or checkpointing or model weights. But somebody gets you so far, and then you take the weights, the parameters as they are at that moment, and then you then shift them to be whatever is useful for what you want. Whether you're working at a different company and you want to train it on your company's data sets, or you're an individual and you want to train it on your own thing. So let's give this maybe another. Okay, we're almost there. Okay, so what we're going to do here is we're going to take our loss epoch and we're going to stop it at 10 steps. Okay, so at 10 steps we have this set of weights. We have step 10. This is our model, which is our nonlinear regression, and these happen to just be the weights and the biases of our model. We're going to run this, and you see that our training loss, it was pretty high, but it only had time to get to like right here before we cut it off. So now we make our predictions. We plot our thing, and you can see that right now it's pretty flat. Like, it's not exactly where we want it to be. But if let's increase this a little bit more. We make this 200. We run this again, and you can see that, well, it's going to be hard to see, but just trust me, these numbers are a little bit different. But here we are at step 210. I forgot why it's 210, so I'm going to have to go back and remember why it's not exactly 200. But we end up with this train state that, oh, you know why? Because, okay, this is important, because I didn't reinitialize my train state here. So it took the 10 steps from before, and it added on another 200 steps. So this is actually something I really like about Flax. So now we're at step 210. We look at our loss function again. It's starting to make it further. We've dropped off more on our training loss. We make a bunch more predictions, and it's starting to get closer, right? So you've seen the shape has changed, and because it's a neural network, it can do a lot of different things. And because it's a big neural network, it can take on a lot of crazy shapes. But in this case, we get to sort of a V. So we're gonna add on another 1,000 train steps. So let's let it go. We're now at step 1,210. We look at our loss function. It's not completely flattened out yet, but it's getting there. We run this again, and it's like getting there. It's getting closer. But once we really just let's see if 3000 does it. Once we get to here and we get to here, we run it again. One more time. Now we're really close. Like we're not perfectly there. We're super close. So what I'll let you do is I'll let you folks take this code and run it with different values. But the reason I wanted to show you this, because while we're doing the large language club, is this last piece of intuition. What's essentially happening in the world now is people are like Facebook with their llama model. They are giving you the parameters as trained up to, let's say, step 4,210. They've already done a bunch of training on a bunch of data, a different set of data than you. They've taken their model and they've had a certain set of weights that they've gotten it up to, and they're like, here, this is yours now. Go do whatever you want with it. And what a lot of people are now doing is they're going, okay, let me now take the set of parameters like that they've given me. Let me load it into my own training loop. Let me pick my own loss function. Let me give it my own data, whether it be the X's and the inputs, and then I'm going to train it. And it turns out that when you don't have access to massive supercomputers like OpenAI, Google, or Facebook, this is the way that you can take a pre-trained model that's already like pretty close to what you want, and then do what's called supervised fine-tuning or fine-tuning to then get it to be really good at what you want to do in your own weights. And this is where a ton of the activity is happening outside of the big companies. It's people that are taking all these models on Hugging Face. Let's say Hugging Face model repository. They're going in and they're going to the model hub. Where is it? I want to show it to you folks. Hugging Face. Let's say llama model. They're going in and this is what they're grabbing, right? They're grabbing all of these model architectures and the weights that Hugging Face and the other companies are giving to them. And they're then fine-tuning it to their own data sets. We're going to do this in probably three sessions because we've covered the very basic bottom building blocks of these models, but we have not talked about the next level up, which is what these model architectures mean in of themselves. But what I do want you to take from this book club, and I'll repeat it one last more time before I take questions, is now you've seen all the basic fundamental building blocks of a neural network. You've seen, you have a rough comparison of why, how to use it, and a Bayesian comparison and to contrast it against. You've seen Flax, which is actually the same framework that's used in Google to train these massive models, really massive models, if I may tell you myself. So Flax is the same framework. JAX is the same computational tooling. You've seen all the different pieces from the model architecture to how to inspect the parameters to the train state to the loss function to the training loop that is used to build every single neural network that's out there. It's literally exactly the same thing that's used to train all these big things that are out there. The things that are different that we have not covered yet is how to put the pieces together in the certain ways. So we haven't covered in detail why you would use a dense layer versus a kernel versus a self-attention head versus this activation function or things like that. And that's what we're going to cover in the future sessions. But with that, that's my like super whirlwind tour of the basics of neural networks. If you want to get into the code, what I really invite you to do is I invite you to go into this notebook. You can run it in Google Colab if you like, and I'll probably add a link later. But I would suggest really understanding this thing here, this training loop, because the training loop is where everything comes together. You've got all the different pieces that all get plugged in here. So understand this on the linear case, and train your own linear models and recover your own parameters, and then try out a bunch of different nonlinear models. So if you want, go into here, try out a bunch of nonlinear models that you can visualize, and start and stop the training at different points, and see what it looks like. And if you get a really good understanding of this, you're going to be well prepared to then level up in the next sessions. All right, so with that, as always, I'm always a little bit over an hour, but let me go through questions. So I'll pull them up. Andrea asks, what is the -- none part supposed to do? Yes, you got it. It reshapes the vector. So I don't want to say it's the fun part. It's actually probably the least fun part about doing all this. Actually, to me, honestly, it's the most jarring and annoying part. But the shapes really, really matter. You have to really get these shapes right. So another thing you can try is go in and change the shapes and see how this whole thing falls apart. See the shape errors, because later on, we're going to be talking a lot about all sorts of different shapes. You're going to get kernels are going to be another thing about shapes. Transformers have their own shape. Embeddings have their own shapes. Softmax has their own shape. And it just, as a matter of practice, if you get really good at navigating these shapes, your life in training neural networks is going to be much, much, much better. So it's not a fun part. It's probably, in my opinion, one of the most annoying parts. But getting a really good understanding of how these shapes work and how to think about them helps you understand what's going on in your neural network, and it really helps you debug your neural networks a ton. So just get comfortable with shapes. Let's see. Do I have any other questions? I don't see any come in. So this is the part of the book club or the study club where I wait about 10 seconds to see if anybody has any lingering questions towards the end. And if there are none, we will end it. But instead of waiting for those 10 seconds for you folks to ask questions with me just staring at the camera, I will highlight again. The community is a really good place to work on this thing. Async. We have a whole Gen AI category where you can go in, and this will fill up with particular questions. We do this because not everybody can show up to a book club at Sunday at 8 a.m. all the time, but we want everybody in the world to be able to learn wherever they are. So going into this community is the way we can all continue learning and working at whatever time we have. Fadi asks, what does .jit do? So I'll pull this up again. All right, so something to know about these neural networks is, especially the big ones, is it's not the model or the math that's making them complex and hard to train. It's that they literally take sometimes days or months to train on full supercomputers. So another area of improving these models is just having them train a lot faster. There's a ton of active work that's being done just to understand how to make the computation faster and faster and faster and faster. So in this case, JAX is a computational framework that speeds up computation for high performance computing. So we need two things. We need a gradient and we need to get it fast. And what jax.jit does is it transforms our Python code into a super fast low-level representation that can be sped up on one core, parallelized on one core, or split and broken up into multiple cores. I want to say, actually, while I selfishly bring this up, I'm contributing some docs to JAX that help explain this exact thing. So it's still in WIP, but you can read about it here. How JAX.jit and how all these things help make the code faster. But it's basically the crux of it is making your computations as fast as possible. So that way we can get through this train curves faster. So rather than having to wait literally maybe 1 month for this, you get a result back in 1 day. So just in time compiling. That's what JIT does. Any other questions? It's a good one. We got a whole bunch of good ones. I appreciate these nitty-gritty questions, right? Because sometimes when you're learning about all this, there's the theory and there's the math, but then there's also the computational side of it. And in this study club, we're going to bring both of them together. We're going to cover the foundational theory with references, but I also want to show you what the nitty-gritty math looks like at its core. Cool. With that, I don't see any other questions. We're at a little bit over time at now 1 hour and 25 minutes. But if you have any other questions, you always have the community forum. I'm always happy to answer however I can. I'm really excited for these next couple of book clubs as we dive deeper and deeper into large language model. Well, more complicated models and transformers first, and then large language models. Nitesh says, does it take less time to run the function from the first call to the second call, or does it take less time from the first call itself? On JAX it takes less time on the second call, because the first call it compiles the function, and then on the second call it reuses the compiled function over and over again. So trying to think of the most succinct way to explain it. In JAX, there's a couple of ways to make things faster out of the box. JIT, I believe, will pre-compile your function, so it's automatically available for then it to be run. So you're getting into a very particular nuance here, whether it's called lazy compiles or eager compiles. If it lazy compiles, it means it waits until the function is called and then compiles it. And then if it's eager compiled, it means that it compiles the functions right off of the bat. This is actually a very important distinction to make, because this is actually the difference between TensorFlow 1 and TensorFlow 2. If you use I don't think anybody uses TensorFlow 1 anymore, but TensorFlow 1 used one paradigm, and then TensorFlow 2 uses the other paradigm. And actually, the way I should have phrased it is that's eager compute versus lazy compute. And I believe JAX compiles the code I believe it compiles it when you call it. I don't actually, so I'm gonna caveat here and say I don't know the details off the top of my head. I know that it gets compiled somewhere, but let me look at the JAX docs, Nitesh, and then I will get back to you and give you a very precise answer. I want to really try hard not to give you folks wrong answers here. So my answer for this is ignore everything. I don't have a specific answer to this question, but it's a very important question that you're asking, and it's commonly a tension between it's a key differentiation between different types of frameworks, whether it eager computes or lazy computes. Yeah. I love these questions, by the way. I feel like these are the ones that can trip you up when you're starting to learn all these frameworks. So if I can get them out of the way for you faster here, then you can learn more smoothly and easily throughout the rest of your time. Any other questions? Okay, great. Yeah, so at least one person learned something new today. That's I'm excited. If one person learns something new, then this time is worth it. If we ever end up with a series of book clubs where nobody learns anything new, then I probably should stop these. But so far, it seems like I'm doing okay. All right. Well, then I will leave it off with the last little bit. What we're gonna do in the next session is we're going to move on to more complicated neural network architectures. We're going to move on to at least talk about convolutional neural networks, recurrent neural networks. I'm going to show you implementations of them in Flax. I'll point you to them right now so you don't even have to wait. Flax has this examples section, and in here they have a ton of super good examples that are already pre-built. We're going to be leveraging these, but here you can already start to see convolutional layers and things like that. Even though this may look a little bit scary, this is just exactly the same Flax code that we were using in our previous in our book club. They're just adding in more stuff, but hopefully this is starting to feel more familiar to you. We're going to be going through, I think, also some of these sequence models for transformer. So here's a transformer one. We'll be using some of this transformer stuff and talking about dropout rates, attention dropout, and you're going to be seeing a lot of similar stuff. Here you're already seeing some of the stuff that we talked about before. Learning rate was how fast we're moving down on things. You can see this particular model took 6 hours to train on pretty serious hardware. So we actually I won't be running this on my desktop computer for sure, but we'll be talking through this. So you can see some of these already here. Accuracy curves. This one doesn't have a lot. Does it have a learning rate? Yeah, it does. So you can see some of these loss curves already, right? That are coming up. So I just want to point out again, it may be overwhelming when you see it in all these dashboards and everything all together, but if you really just understand these blocks, you're going to have a really solid foundation to then start learning the more complicated architectures that we're going to jump into the next session. So that's all I have for today. I think most importantly, I wish everybody a happy Mother's Day, and I hope you wish your mother a happy Mother's Day, whether you live in the U.S. or not. I am not seeing any other questions come in, but I am happy to take any questions async. So thank you for spending another hour and a half with me here again. I know today was a fast session where I walked through a lot of things, particularly quickly, but we're always here as a community. Yes, let me share that to you. We're always here as a community to learn together. You have the I can't not post. You have a link to the async community where we're chatting with things async, and by the end of this, we're going to be really good at learning and understanding how to train these large language models on our own, and getting through the hype and getting to the useful part of using them for what we want them to do, not just what other people are telling us they want us to do with them. So that's all, folks. I wish you again a happy Sunday, and we'll schedule the next session. I think it'll be a little bit longer, probably 2 to 3 weeks from now. Probably 2, but maybe 3 weeks from now. So we'll take a little bit more of a break here. All right. Thank you again, and I'll see you in a couple of weeks.